Hi everyone, welcome to another tutorial. In this video we're going to be taking a look at path transversal vulnerabilities in Python Flask web apps. So I'm just running a virtual machine here, Ubuntu 22.04, and to get started we'll just open up a terminal and we'll need to download some packages for this demonstration, which you can do with the sudo apt-get install ssh python git pluma and Apache 2, and just hit enter. If you're just installed a fresh machine, this will take a couple of minutes, but I've already done this, so yeah, we can just open up a browser, and I've created some vulnerable Python code on GitHub, which you can just download from there by going to github/darkside-security, and it should be this first link here, python-lfi. We're just going to click copy the link, navigate to the downloads folder, open up a terminal and go git clone followed by the link. So that should be cloned for us, and I've just written some Python web apps in Flask with some local file inclusion vulnerabilities. The first one here has a reflective path transversal vulnerability in it, and the insecure upload that has a blind LFI bug in it. So I'll just be demonstrating those vulnerabilities, how to exploit them, and how to protect and mitigate against them afterwards as well. So the first thing we're going to do, we'll need to install some repositories, some dependencies actually, by going pip3 install -r, and you can just copy in this file afterwards, and that should install the repositories for you. Now to run the application, just go python 3 lfi.py, and that should host the application running on these interfaces here. And now let's just go over to the attacking machine. I'm just running Kali here. Just open up a terminal, and we'll just run an mmap scan to figure out what open ports are running on the target. So just go nmap 10.1.1.187. This will be a little bit different for you, so just copy and paste the IP address. So we'll just wait a couple of minutes for that to run. Open up a web browser, navigate to the IP address of the machine, and it's running on port 8000, and you can see where we've got a web server here. So I'm just going to click around and see what we can see on the application. Looks like I've got a text file that says filter./ so that's a clue we could be dealing with a path transversal vulnerability in that application. So I'm just going to have a look at that mmap scan, see if that's done. And while I'm waiting for the mmap scan to finish, I'm just going to open up Burp Suite, just so I can send some requests and have a look at the server response. go over to proxy, open up the plugin Foxy Proxy, enable burp. So now we should be, it looks like mmap scan is done, so it looks like the target's running port 22, SSH, version 8.9 P1. They're running a basic web server, running Apache 2.4.52, and we've also got port 8000, which is our Python web application, running version 3.10.6. So we've got 2 web servers running, just so we can know what we're kind of testing. So it looks like we've got an import file here. I'm just going to enter test. Looks like it says test is not a directory, so it looks like it's just basically opening up whatever path we give it. Just go over to proxy, so you can see the request here. Got a parameter called search, and it's taking in some input. Looks like a GET request, so we're just going to right click, go repeater, click on repeater, so we can send numerous requests, and we'll see if we can find a vulnerability with it. So I'm just going to go /etc password to try and get a list of all the users on the target system. Press send, scroll down, looks like it has echoed back the etc password file, so we've got a list of all the users on the system. So it looks like we've found a path transversal vulnerability in that Python web application. So yeah, this is basically just a echoes back some input. And I'll just go back over to the target machine here, and I'll just show you the source code for this application. So you can see it's taking in a GET request for a parameter called search, and I've marked down exactly where the vulnerability is in this application. LFI vulnerability basically takes in raw unsanitized data and doesn't apply any filters to it. So basically whatever path we give it, it's going to open that file and return it to the application, which we saw printing back the etc password file as well. And I'll just show you some other paths as well. So we could do var log apache 2 access.log. See if it gives us any return on the Apache log file, and you can see we've got some data here. Now if this web server was basically running PHP, then we could try and poison the log file and get a reverse shell through the user agent, but of course Python doesn't run PHP, so we can't really do much there. And I've included a fix as well, so we'll just have to change the URL to /fix, and you can see to fix it you just need to import a library called workzerg.utils, which is a built-in library in Flask, and it's importing secure file name. So secure file name basically strips the .. from the actual inputs, and then it will echo back basically whatever's in the file. So I'll just show you that one as well. Just close this terminal. And the next application we're going to run is insecure underscore upload. That's running. Go over to the attacking machine here. I've just got to open up the index.html and just edit something. You can see it's got a parameter called search. We're just going to change that and just enter fix. Restart the Python web application. Go over to the attacking machine, open up the browser. So you can see we've got a secure file to upload. So let's try and upload a file. I'm just going to use burp again. Click on browse. We'll just need to create a file. Create document test. Just going to save that. Click on test. Submit that. So that's gone through to burp. We can see a post request going to the endpoint upload and just some application data with a file name named test. So we're just going to send that and see what the application responds with. Looks like it says upload successful. So we know that is successful, but we don't know where it's been saved to or if we can actually access it. So sometimes with Python web applications, if they wanted it to be visible, then you could sometimes go to static and then test.txt if they haven't modified the file name. Looks like they haven't set up a route, so we can't actually view any files that we saved to the server. So normally if there was a PHP application, we could just upload a PHP shell, visit the upload directory and get a reverse shell back. But in this case, we can't actually do that. Essentially because the application isn't running PHP, because it's running Python, and number two, we can't actually visit any file we upload to the directory, so that won't work as well. So this is what's known as a blind path traversal vulnerability. It's blind because it doesn't give us any it doesn't echo back any data to say where it's been uploaded to or any information like that. So this is generally one of the more difficult vulnerabilities to exploit from an attacker because they don't have any indication that the exploit has worked. So they will just have to try different methods to see if they can actually exploit a vulnerability. So it's going to take them a while. So let's take a look at trying to exploit this vulnerability. If we go over to the victim machine here, go to uploads. We can see we've got a file called test.txt. So yeah, that file has been uploaded to there. So let's take a look at what we can do to try and exploit this machine. And if we have a look, looks like they've got another web server open on port 80. So, and looks like they're running Apache. So Apache runs PHP on the machine. So we can try and get a PHP reverse shell on that web server, and we should be able to compromise that machine through that method. So let's try and do that. It should be noted that this is only going to work if we have right permissions. If we don't have right permissions, then it's just going to give us a fail status. So just going back to this request here. First of all, we'll need to generate a PHP reverse shell. So just open up a terminal and go msf venom -p php interpreter reverse tcp, followed by the local host IP address. So if you didn't know what that was, just open up a terminal and go if config. As you can see, mine's ends in 125. Yours will be a little bit different, obviously. And I've set the L host as 443, which you should know is the HTTPS protocol, just to disguise a little bit different. For the format, save it as raw, and as the output, I'm just going to put it down as shell.php, but you can call it whatever you want. So that file should be done. I'm just going to open it. For some reason it's been putting in the wrong information lately, not too sure why, so I'm just going to put the IP address in manually and change the port to 443, save it. Go back to the terminal here and open up MSF console, Kali, or whatever your password is. So we're just going to open up a multi-handler to try and catch the session. To do that, you can just do use exploit / multi and handler. And we're just going to copy this payload here and go set payload, copy and paste that payload in. So it's listening for a PHP mid-interpreter session. Set L host, just go eth0 or whatever the adapter interface is running on here. Set L port to 443 or whatever port you used, and then just hit run. So it's just listening for any incoming connections coming from the outside. So if you do get a shell, then we're going to get a session here. Now we're just going to go back over to Burp Suite. Actually, we'll need to upload this application again for the new file. Try and upload shell.php. Catch the file again. Center repeater. As you can see, it's got our PHP code here that we want to run, as well as the .php file name. So if you're wondering how do we get this shell onto the secondary web server located in a different directory, so essentially what we're going to have to do, we're going to have to step back all the way to the base of the root of the directory, and then we're basically going to have to go forward. So we can do that by going .. we're just going to have to put in a whole bunch of them because we don't know how many directories that are on the server. So with path traversal, you can only go back a certain amount of times until you basically hit the root directory, which is basically just slash. And then from there, you can just go forward to wherever you want once you've actually reached that point. So that's essentially what we're going to do here. I've put in a whole bunch of backslashes, so we should be at the root directory now. And now we're just going to go forward, so we'll just be going to var /ww/html, which is basically where the secondary web directory is. And we're just trying to copy that shell file into the directory. So we'll see what happens. And it looks like it's given us a permission denied error on this application here. So obviously if this is a real world application, you wouldn't see permission denied. It will just come up blank and you would have no idea what's going on. I just did this to help out with exploiting the application. So I'll go back to the target machine and just close that. And so the idea is if the target is running this with elevated permissions, we could actually exploit that application. So if they ran it with sudo and then the application, obviously you probably wouldn't see this in the real world. You'd probably see a service account or something like that being run, but if this did happen, then you could exploit this bug through that means. So this application is now running with sudo permissions. So now we're just going to go back to the server and do the same request, and we'll see if we get the same response. And you can see it says upload successful. So looks like we do indeed have sudo permissions. So let's just navigate back over to the server and go back to 187 slash shell.php, and I'm just going to have a look on target machine, see if that file is there. And yes, we've got a shell PHP, so it has been copied successfully. I'm just going to go back to the session handler. So once I click on this, we should have a remote session into the target. And looks like we've got a meta-interpreter shell. And so I'm just going to take a look at what our current privileges are. You can do with get UID, and we're currently running as www-data, so we're not running as a privileged account. So I'm just going to drop into a shell and I'm just going to see if there's any privilege escalation flaws that we can exploit to get root. So I'm just going to background this session for a minute. And I'm just going to search for a post module called exploit underscore suggester. So I'm just going to run this to see if there's any privileged escalation misconfigurations that we can exploit. We just need to give it our current session, which is 1. So we can do set session equals to 1, and then hit run. And this will just gather all the privileged exploits for PHP and Linux that it has in its database, run them against the target, and it will let us know if there's any exploits available to us. So it looks like there's 2,332 possible exploits. Essentially, these are pretty much all going to fail. But if the system did have a misconfiguration, you might be able to find it through this method. As you can see, that's failed, so we're just going to go back to our session. Just go sessions, -I, and 1. And we're just going to go back to our shell here. And one command we could do to try and find privileged escalation bugs, to see if there's any SUID binaries that are basically misconfigured. You can just enter the command find \_perm -u equals s -type f 2 greater than \dev \null. So what this command does, it basically looks for any binaries that have the sticky bit flag attached to them, and if they do, then we might be able to try and exploit them to gain a root shell on the system. So you can see we've got a few of them here. As you can tell, we've got one called the user bin bash, so we should be able to exploit that to get a root shell on the system. So I'm just going to change our interpreter here. Just go bin bash -I, and now to exploit this vulnerability, we can try bin bash -p, and -p just essentially maintains the elevated privileges so it doesn't drop down. So if this was running as root, then we're going to get a root shell. type in who am I, you can see we're running as root now. And to prove that, we should be able to get access to the etc shadow file. And we've got access to the etc shadow file, which has all the user password hashes stored in here. So we could brute force these and get access to other accounts, but because we're root, we can just reset the password for any account on the system. So we pretty much have universal access to the whole machine now. So that's an example of how you could compromise a system through a Python web app vulnerability and get root access on the system. Now there's one other possible vulnerability that I've thought of, but requires a little bit of additional information to exploit, so we're just going to take a look at how to do that. So I'm just going to exit out of the Metasploit framework because we don't actually need it anymore. So just going back over to the target machine here. Just going back into the directory. So we're just going to be running this application again, just with lower privileges. So the second exploitation method, utilizing an SSH private key. We should be able to do this with lower privileges, assuming we have right directory. So just go back over to the attacker's machine here. Go back over to the Python web application. And basically what we're going to be doing here is we need to generate a SSH key pair. So I'll just delete my files here. Open up a terminal and go SSH dash keygen, and this will create a public and private key to access a SSH server with. So that should be done for us. Go over to .ssh, copy the public and private keys. And what we're going to do here is open up a terminal. We need to create a new file called authorized keys. So to do this, just do touch authorized underscore keys. Let's create our file for us. Now we're going to need to copy this public key into the authorized keys directory. To do that, we can do cat id underscore rsa.pub greater and this greater than symbol just puts all the information into the authorized keys file. Hit enter. Now if we open that up, we can see we've got the public key in that directory. So this is going to be our exploit file. We're going to try and overwrite the current key set on the Ubuntu machine. So if I just go home .ssh and they've got an authorized keys file here, and you can see it's got the Ubuntu machine public key here. So essentially, if we can overwrite that file with this key, we can essentially get access to the server through SSH. So going back to the attacking machine here, open up a web server, just upload that authorized key file, which is in the downloads. Click submit, go over to repeater, and you can see it's got a public key here. So similar method to what we did before, we're just going to go to the base of the directory, and then we're going to go forward into that folder. So the only downside with this exploit method is that you'll need to know the actual user you want to write the directories to. So obviously, if you don't know what the user account is, then you're not going to be able to exploit this system. I think so you might be able to do some enumeration trying to find that out. I think there used to be, there is a module in the Metasploit framework that allows you to enumerate SSH users. But if they're running a up-to-date version, then you're just going to get a whole lot of false positives. But I will just run that module so you can see. Just type in SSH enum. We want to enumerate the users. Use. Go to options. We just need to set the IP of the server. And we want to leave check for false positives on, and we're just going to set a username here. I already know what the username is, which is Ubuntu, but if you didn't, then you could just use a file list and try and find it out that way. So I'm just going to run this, and it looks like we're getting false positives, so I can't actually identify it. If the target was running a vulnerable version to SSH, maybe that might work, but yeah, it's going to be a bit of trial and error, I reckon. But as for the demonstration, so we just need to go put in some / slashes to go to the base directory again. Then we'll need to go home, Ubuntu .sh, and that should overwrite the existing authorized keys file into that directory, or if they didn't have one set up, then a new one will be created, and we can still get access to the server through the private key. So let's have a look. It says upload successful. Just go over to the target machine here. Click on authorized keys. You can tell it's been changed because it's got Kelly at Kelly. So we should be able to compromise that machine through an SSH connection now. But before we do, we've got to change the permissions for the private key to 600. To do that, you can do gmod 600 and just do ID RSA, which is the private key. And now we're going to try and log into that user, so we can do SSH, the user Ubuntu, the IP address followed by -I ID underscore RSA. And you can tell that works. We've got SSH access to this user account. So I'll just go who am I, ls. So you can tell we are indeed on the victim machine here through SSH. And the only thing I will note, if you when doing this this exploitation method, essentially if they did have authorized keys here and you overwritten the file, the owner of the machine is going to get locked out. So basically you're going to have to recopy this public key into this authorized key file here, so both you and the existing user has access. Otherwise they're gonna know that you know, they've been compromised and that kind of stuff, just to keep in mind. So we should still be able to get a root shell, exploiting that bin bash command. Who am I? And you can tell we are root, so we've completely owned this machine through a SSH key write method. And again, if you're exploiting this machine out in the wild in real life, then obviously it's this would probably be a little bit more trickier, and you're probably not going to have write access, but I guess there's always a chance that someone could have misconfigured it, so I suppose it could happen. So that's pretty much it for the exploitation part of this video. Now, just to finish things off, I'll just show you how we can patch these vulnerabilities, just starting with the first LFI file here. I've just noted down all the parts of the code that are vulnerable. You can tell here it's opening a file, it's taking a GET request from a parameter called search, and then it's opening that raw command without any sanitization. And I've just noted here LFI vulnerability, unsanitized data. And I've also got a potential information disclosure vulnerability here. I've just, if we get an exception, so if the upload fails, it's going to tell us why. This was just done for developmental reasons, and also to help you exploit the machine. Obviously, if this was in the real world, then you wouldn't use this. You would just backslash it and go backspace it and just put in failed. So if it fails, you're just going to get a response printed to the screen called fail, and then it wouldn't print any permission errors or anything like that. So just something to be aware of. And the fix for this is actually pretty simple. We just need to import a file called workzerg.utils, which is a built-in library built into Flask, and we need to import the library called secure file name. And essentially what this does is we're going to create a new variable called file path equals secure file name, and we're just going to put the basically the GET request into that command, and that's going to strip the // from the actual application. And so essentially if we try to put in /etc/password, it's going to return the file etc password, which of course isn't in the directory, and it's just going to fail. So to demonstrate this, just go to template, open up the index file into a text editor. Change the action path to that's already on fix, so that's good. Just go over to the target machine, go over to the browser, just go back and execute the LFI file here, go back over to the attacking machine, open up a browser, navigate to this directory, and just type in what we typed in before, etc password, and as you can see, it stripped the slash from the actual file here. So if we try to go dot slash etc password, it's going to print out the same information on it. And you could also do URL encoding and stuff like that, which I've already tried this, and that doesn't bypass that either. So that is essentially how you fix an LFI vulnerability in that application. So the next one we're going to have a look at is the insecure upload.py, and this one's a little bit more complicated. So I've just noted down some configuration issues that weren't set. So for instance, no file limit was set, so you could upload a file as big as you want. So it could be a 10 gig file. So if you're uploading multiple 10 gig files, obviously that's going to consume disk space, and it could cause a denial of service attack on the web application, or it could just fail because it doesn't have enough space or memory. So generally you always want to set a file size depending on your application. It could be something like 25 meg or something, 5 meg, depending on what applications you need to serve. And the second vulnerability is it doesn't have an allow list. So usually with an allow list, you want to define what extensions or file types you want to allow. This could be .jpeg, .pdf, Word documents, anything like that you want to allow. So anything that's malicious gets rejected straight away, which is a good way to keep your file upload application safe. So just looking at the source code here, it's taking in a post request with a parameter called file. It's storing the file, file name in a variable called file name. Then essentially it's saving this to a directory called uploads plus file name. So essentially it's just appending the writing the file to a uploads directory called uploads, and just storing in there pretty much. So I've noted down that it doesn't sanitize the raw data coming in. It just writes basically any file that you give it to the file system, which obviously could be malicious, and you've seen that as we've exploited the application twice. And a third vulnerability is this information disclosure leak. Essentially, is printing out an error message when it fails. So this could give an attacker more information about how the application works, and if they know how an application works, then it's going to be much easier to try and exploit it, especially if it's a blind vulnerability. So fixing that is obviously pretty simple. You can just go /response just restart the application here, go over to the attacking machine, load up the web browser. Looks like I just mixed up my files here. Just a sec. Just going to echo out this file string if it fails. Let's see, password. So it's just going to echo back fail. So obviously if there's a real web application, you probably wouldn't put fail or anything like that. You'll probably just put it as blank or put it as none, and then it'll just basically not return anything, so it wouldn't give the attacker any more information than it should do. And so basically to set a file limit for this Python Flask web application, just go app.config, and we're going to define a list here. And all in caps, call it max _ content _ length. So this basically sets the max length of a file, and probably just going to do 1024 times 1024 because it's in bytes. And the next one we're going to do is we're just going to define an allow list. So just go app.config, define a list variable, upload _ extensions, equals, and then you can define what extensions you want. I'm just going to do JPEG. .png, and maybe a .pdf there. So the first thing we that we want to do here is just copy over this library file here, and similar to what we did before, we're just going to secure this file name just so it's URL safe. So basically what we need to do is just call a function called secure underscore file name, import that as the object, and that essentially is going to strip the // and also any URL characters like percentages and stuff like that that it sees. And next, what we're going to do is going to create an if statement called if file name not equal to space, create a block, and then we're going to create a new variable called file underscore ext for extensions. Import another library called OS, and we basically just need to extract the extension from the actual file name. So to do that, we can do os.path.split text, and the variable that stores the file name, which is called file name. And then we're going to do a slice, which basically the file name is located at 0 and the extension is located at 1. So that's just going to extract the file name for us into a variable called file underscore ext. Now we're going to create a new variable called response equals, and you can just, this is just going to be the string you want to echo back to the user if the upload fails. So just go file type not allowed, or whatever message you want to convey. And the next one we're going to do is we're going to render that response. So to do that, we can do return render underscore template, and the first thing we need is a HTML file, which is just going to be this insecure uploads file. Comma, and we're going to create a new variable called data, which just reflects the information back to the web page. So basically, whatever information is stored in this variable response is just going to reflect that back to the user in a variable I've created in the web page called data. Now the next thing we're going to do is we need to create unique file names. So essentially if users start uploading files and they're the same file name, they're essentially going to get overwritten. So to do that, we can import a library called UID, which basically generates unique basically strings that we can rename the files to. So we're just going to create a new variable called unique underscore file file names. And then we're just going to create a string. So you can just do that by going str parentheses and then UUID dot UUID4 and then a function call after it. So this should generate our unique strings for us. And next we have as where we save the file into the directory. So I'm just going to rename this file name into unique file name. And after that, we're just going to return the template. Render underscore template just copy and paste the HTML file that we want to copy there. Add a comma. Data equals response. So we're basically telling it to echo back the response, upload successful. And the next part of that is if we get an error, echo back a string. So I'll just change this back to format string, curly brace, str, function, e is an object. So if we get an error, just echo back whatever the error is. And that should be pretty much all we need to fix the file. So I've already done the application here. I've basically just rewritten it just so you can see kind of how it all falls into place. But essentially it extracts the file extension, checks if the file ext is not in uploads, and essentially then responds with a response file type not allowed, then renders the render response in the HTML, and then if that's if the file name is in the extensions here, then it's going to go ahead and change the file name, save it to the upload directory, and change the response. So I'm just going to execute this secure underscore upload and go to the attacking machine here. And we're going to see if there's any differences in the application. So I'm just going to try and upload a file here. Let's say authorized keys, submit, file type not allowed. Let's do shell PHP, file type not allowed. I'll see if we can do some evasion techniques, just to see how good the filter is. Submit, send to repeater. Let's just do dot JPEG, null bytes dot PHP, file type not allowed, so that doesn't work either. And I'll just upload a photo, see if that works. Upload successful. Let's go back to the uploads file, and you can see it's created a random string for the file. So that's clearly been changed. So if the user did have access to these upload directory, they would have to brute force this file name just to figure out what file it is. So it's a little bit more secure in that sense. And you can see the file isn't still intact on the server. I think the only thing I forgot to put in this original fix was the if statement, I'm pretty sure, which to do that you can do if file underscore ext not in app.config just refer to this upload extensions. Underscore extensions. Create a block for the if statement. And that should filter out the file names. So that's pretty much all you really need to do to secure Python web apps. And if you can think of any other exploitation methods for blind LFI for Linux systems, let me know in the comments. But yeah, that's pretty much wraps up the end of the video. And yeah, I hope you learned something. Thanks.